In this experiment, a spring system was released from rest into motion. This was done to test the validity of Newton's second law and the energy principle, which relied on gravitational potential energy, spring potential energy, and kinetic energy in this experiment. The object is being dropped from rest, and the only forces acting on the object are the weight force, spring force, and damping forces, which we will assume to be negligible, as will be shown in our model. To obtain empirical evidence of these forces, I use the program Tracker to track the object and get a series of points that follow the position of the object. From there, I created a model in Python of the predicted motion. I then compared the predicted motion to the actual motion to verify Newton's second law, and the change in the total energy to verify the energy principle. Both principles were verified because the prediction closely matched the actual data, and there was no change in total energy as the individual energies changed. To create an accurate model in Tracker, I set the initial length of the spring in the background to give a scale to the video. Thus, by inputting this into Tracker and marking the center of mass in every frame, Tracker was able to output the position meters for every frame, which was 1 over 10.5 seconds. Now, with regards to making our model in Python, in this first block of code, we set up our graphics for the prediction simulation. Then I set the initial conditions including k and L naught. I set the oscillation of the y period equal to 2 pi times the square root of m over k to obtain k. Then I set the gravitational force equal to the spring force when the object was hanging at rest to solve for L naught. Next, F net is found by summing the spring force and the weight force. Then, I use Newton's second law in a loop to predict the changing velocity of the object and the position equation to predict the changing displacement. I then calculated the new energies and the changes in energies, which will be plotted on the graph. Due to the energy principle, the sum of the changes of the individual energies equal the change in the total energy. And finally, here is the model. For your model, is the energy principle satisfied? Yes, we can see that energy is conserved from our graph of the energy since the total energy change, the yellow line, remains constant. Also, we see that our prediction is accurate due to the motion of the objects, the red ball being the observed data. There is a slight discrepancy in the position of the objects due to inaccuracy of measurement, errors placing the center of mass in Tracker, and not accounting for dampening forces. Using the data obtained in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. The period was found by averaging 3 of the time intervals in between the peaks of the oscillations. From this, I saw that the x and y periods were completely independent of each other. This was because the y component was acted on by the gravitational force as well as the spring force, while the x component was acted on only by the spring force. Also, the x and y components of the spring force are different. From this experiment, the energy principle and Newton's second law were verified by the Tracker analysis and Python simulation. This was shown since the prediction, which was calculated by Newton's second law, followed the same trajectory as the observed data, and the change in total energy remained at 0.